Welcome to the Explainer. Today we're diving into the simple physics behind basically everything that wiggles, swings, and vibrates. You know, from the tiniest atoms to the grandest galaxies, there's this universal rhythm that connects them all, and we're going to decode it together.
Okay, so let's jump right in by looking at some movements you see all the time. They all share this kind of secret connection. You see them every day, but you might not have realized they're all, playing from the same sheet music, so to speak.
So picture a block attached to a spring. You pull it, you let go, and it just keeps on going, bouncing back and forth, right around a central point.
Or, hey, think about the steady, rhythmic swing of a pendulum. You know, like the ones in those old grandfather clocks? That calm, predictable arc? Yep, that's another perfect example of this fundamental kind of movement. It turns out this to and fro motion, which we call oscillation, is absolutely fundamental to understanding everything from the sound of a violin to the light that's reaching us from distant stars. It's one of the most basic and most important concepts in all of physics. To really get a handle on this, we've got to build up our vocabulary with just a few key ideas. Once we get the language down, I promise you'll see how simple and honestly how beautiful this all really is.
First up is periodic motion, and this is any motion that just repeats itself in a regular cycle. The easiest example? The Earth orbiting the Sun. It makes one full trip every year, just like clockwork. That's periodic.
Okay, now, a special kind of periodic motion is what we call oscillatory motion. This is specifically a back-and-forth movement around a central point of balance or equilibrium. That swinging pendulum, that's classic oscillatory motion.
So here's the crucial point, the main takeaway. All oscillatory motion is periodic because, well, it repeats. But not all periodic motion is oscillatory. The Earth's orbit repeats, right? So it's periodic. But it doesn't swing back and forth around a center point. It just keeps going around. That is the key difference.
So how do we measure these motions? We use their period, which is just the time it takes for one full swing, and their frequency, which is how many swings happen every second. They're just inverses of each other. So a long period, a really slow swing, means you have a low frequency, and a short period, a super fast wiggle, means a high frequency. Simple as that.
All right, let's build on that and look at the most fundamental type of oscillation there is, simple harmonic motion, or as we call it, SHM. This is like the perfect, idealized wiggle that's the blueprint for all the others.
Now don't let the math on the screen scare you. All this equation is really saying is that the position of the object, that's x, at any moment in time, t, follows the smooth, predictable, repeating pattern of a cosine wave. It's just the math for a perfect rhythm.
So what causes this perfect motion? It's a special kind of force, called a restoring force, that is always pulling the object back to the center. And here's the cool part. The force gets stronger the farther you pull the object away. It's like having an invisible, perfect spring that's always trying to get things back to balance.
Now here's where it gets really cool. We can actually visualize this complex-sounding motion with a super simple and elegant analogy, and it reveals this hidden link between two types of motion we thought were completely different. I want you to imagine a particle that's just moving in a perfect circle at a perfectly steady speed. Just a simple, continuous loop. Nothing special, right? But what happens if we shine a light from the side and only watch its shadow on a wall? As the particle goes round and round, what does its shadow do?
You got it. That shadow just moves back and forth in a perfect straight line, exactly matching the pattern of simple harmonic motion. This is so cool. It reveals this hidden connection. SHM is just the one-dimensional shadow of perfect circular motion.
So we know how it moves, but what about the energy that's driving it? I mean, in any closed system, energy can't be created or destroyed. It just gets transformed. And in an oscillation, that transformation is constant and kind of beautiful.
Think about it. At the extreme ends of the swing, the object actually stops for a split second. At that moment, its kinetic energy, the energy of motion, is zero. At that exact point, all the energy is stored up as potential energy. It's like the energy in a stretched spring or a pendulum at the very top of its arc. It's all coiled up, just ready to be released.
And then, whoosh, as the object rushes through that central equilibrium point, it's not stretched or compressed at all. It's been let loose, and it's moving at its absolute fastest.
And at that center point, all that stored potential energy has been converted into kinetic energy. The total energy always stays the same. It's just in this constant dance, trading back and forth between potential and kinetic.
So this simple back-and-forth exchange of energy in SHM, it's way more than just a textbook concept. It's a fundamental building block of the physical world. It scales up from simple things like pendulums to create much, much bigger phenomena.
And this is where it all comes together. A wave is really just a chain of connected little oscillators passing energy to one another. So when air molecules oscillate together, you get sound. When electric and magnetic fields oscillate, you get light. When the ground itself vibrates in this pattern, you get an earthquake. It all starts with that simple wiggle. So, the next time you see something swing, or vibrate, or even just hear a sound, remember the powerful physics at play. And it makes you wonder, doesn't it? If the universe's most complex waves are built from this one simple wiggle, what other complex systems out there are just simple, elegant rules repeated over and over again?